Hello everyone, welcome back to the session on your operating system. So in today's session, we'll be starting your fresh unit, okay, of your operating system. That is nothing but your unit 4. And in this, we are going to discuss about something called as process synchronization. Okay, so let me give a brief introduction related to process synchronization before we dive into the different topics what we have relevant to this particular topic. So well, basically, in the third unit, we discussed, okay, in unit 3, we discussed about something called as cooperating processes. If you people remember the cooperating processes, we discussed about something called as how they can communicate with each other. So we discussed about something called as shared memory. And another one that we discussed here, something we call it as the message passing, if you remember it. So here the main concept what we are going to discuss about is the shared memory. Means exactly what it means to say in this particular scenario here is that just a minute. Yeah. So here the thing, what is saying about process synchronization here is that when two processes, let us suppose P1 and P2, communicate with each other, they wanted to communicate on a single project, so they may require to access information from a single file, this particular file. So both of them, both the processes are going to access information from this particular file. We basically go, okay, this is what we call it as a shared file. And within these two processes are trying to access the information. Well, these cooperating processes can either directly or indirectly may affect each other. Okay, they can directly affect each other or indirectly may affect each other. So they can share the resources. Okay, so basically whatever the resources these particular files are going to access here, these particular shared file, whatever I'm talking about, this can be represented in two ways. Either the sharing can be done using a logical address space, or that can be shared using files or messages. Okay, so this particular process P1 and P2, they can try to cooperate with each other by using a shared file, and this file can be represented either in the two ways. That is what we call it as logical address space, and another one is what we call it as files or messages. Well, we are concerned about this particular. We are going to discuss about more about this particular logical address space because this is the one most practically all the operating systems will be focusing on or will support it. Okay, so in this particular thing, let me try to clear the slides here. Yeah. So basically, okay, let me before explaining that particular information, let me provide you the different contents relevant to it. So the first thing what we are going to discuss in this particular process synchronization mechanism is background. And okay, so what exactly you mean with process synchronization and how we are going to access information within that and what is the main purpose of this process synchronization that we are going to discuss it. Mostly in your mobile phones operating system, you might be seeing that it many times it will ask you to synchronize your mobile contacts with your Gmail. Right. So what do you mean by this exactly synchronization? That I will tell you in this brief in this particular background related concept. And then we have something called a critical section problem. Well, this is an important topic relevant to your this particular unit, the critical section problem. And based on this particular problem only, we are going to discuss about the remaining topics, whatever you are seeing. Means there is a problem critical section. So we are going to discuss briefly about what do you mean by critical section and what is the problem associated with that. And for that problem, how we are going to design different solutions. The best solution for this is Peterson solution here. Okay, so this is what. So in today's session, we'll try to cover the background part, the critical section part, and as well as the Peterson solution. And after that, we have some synchronization hardware. This is also a solution. These are also the different solutions related to your critical section problem, but these are not relevant to not only what we call software, these are software and hardware. Basically, mostly these are hardware related solutions will be provided for critical section problem. But if we talk about this Peterson problem, this is purely software based solution. This is purely a software-based solution, what I'm going to discuss in this particular Peterson solution. And coming to process, I mean synchronization hardware, we have mutex clock. This also comes under this synchronization hardware. This is a hardware solution for your critical section problem, whatever we are having here. For this particular critical section problem, mutex clock is another kind of solution. How this means the people have actually provided, but these solutions are actually based on hardware, okay, not based on software. And then we have semaphores. Well, this is a software based Okay, so this is the overall problem, whatever the problem we are facing related to this critical section problem can be overcome by using semaphores. And we are going to discuss about some classical problems related to this particular synchronization. As I told you, what exactly the synchronization problem is, that we are going to discuss, and what are the different classical problems we have associated with this particular topic is what we are going to see here. We are going to see some different kind of examples, and these are very, very important and most famous examples we are going to see, like something like, dining philosopher, like dining philosopher's problem. And then after that, we do have something called as reader-writer problem. This is also one of the traditional problem what we have. Based on that only, the operating system has been designed. Reader-writer's problem. Okay, and the one which you already people know about, we are going to discuss in a few seconds. That is your producer-consumer problem. So these are some of the basic problems that we are having. So for these problems, we are going to see this. We are also going to provide solutions using the semaphores concept. That's the reason we are actually implementing semaphores, and then we are discussing the classic problems of the synchronization. And once that is done, the final what we have when your part one is your monitors. And now this is also for overcoming the problems related to your critical section problem, but monitors are much more efficient. These are much more efficient than your semaphores. Yes, these are much more efficient than semaphores, and within the monitors, we are going to provide a basic solution. Now we are going to provide a solution for this dining philosopher problem. Well, we will see with respect to semaphore solution, same way this model. Well, these are different methods that have been actually provided by the scientists so that we can overcome this particular synchronization mechanism. Okay, now the first question is what exactly mean by synchronization? Let's just discuss about synchronization. Now let us suppose, let's take example that there are two processes here, P1 and P2. And these two processes are actually communicating on a project, some kind of project, and both have to work on that. Okay, let us assume that these are the two different scientists who are working on a similar project. So whenever some updates are performed by any of the scientists, that need to be reflected to the second scientist. Means if the project means this particular scientist is performing some modification, that should be seen. That should be able to be seen by this particular another scientist. So that is what he's saying about. Now here, technically, what we can say that there are two different processes which are actually communicating, which are actually cooperating with each other on one particular task or one particular project. So definitely they have to share this files. They actually have to share this particular files, isn't it? That we have seen in the, that will be saying on the fifth unit where we have discussed about something called sharing of files, means how the particular cooperating process can share in the directory structures we have discussed. Now these cooperating processes can share this particular project either in using a logical address space. Either they can use a logical address space or they can use a normal mechanism of sharing a common files or sending messages in between in order to perform the action. But basically, we will be concentrating on this particular logical address space. Now, whenever a cooperating two processes are trying to cooperate using this logical address spaces, what happens here? If both the process P1 and P2 simultaneously try to perform an option, try to perform any operation on a file, that may lead to inconsistency. Okay, so whenever both the process, let us suppose whatever the file we have, project file, both of them are simultaneously trying to access this file and trying to perform operation on that with this particular file, whatever this particular file whatever we are having, then what will happen? There will be a data inconsistency. That will lead to a data inconsistency, because let us suppose this process P1, okay, we have P2. P2 is actually open this particular file for reading purpose. And at the same time, this particular process P1 has opened the same file for writing purpose. Now what will happen? Whatever the modification this particular process is going to do in this particular file, that will not be reflected when the process P2 is reading, because both of them are opened the file. When both of them open the file at the same time, it consists of 3 lines of code, let us suppose. Now P2 is reading these 3 lines of code and P1 is modifying these 3 lines of code and converting that into 5 lines. But these 5 lines will not be reflected in this particular reading. Why? Because they have opened the file simultaneously. Now there exists a problem here. What is the problem here? That what is the file whichever this processor are sharing, that is not perfectly being implemented. That is the main problem we are having here. So to overcome that, we require some kind of mechanism, and that mechanism is what we are talking about: synchronization. So we need a synchronization between P1 and P2 so that whenever any of the process is trying to modify a file, that modifications are reflected to that particular process. Means whenever he is converting, P1 is converting a 3 lines code to 5 lines, even though he is reading, this process is reading, he should be able to see the 5 lines of code rather than the 3 lines of code dynamically also. That is what we call it as synchronization. So how these operations, whatever these processes are performing, and these operations we are letting to execute one after another is what we call it as process synchronization. And remember, this will be taken care by the operating system, not by us. We are not going to perform that. It's the operating system who is going to perform this particular operation. Okay, so that is what we basically call it as process synchronization. So the main reason why we are discussing this particular topic is we want to make sure that there is no data inconsistency taking place when some processes are trying to access the information simultaneously. Whenever they are simultaneously trying to access the information, okay, simultaneously they are performing the operation, there should not be any kind of data inconsistency, and that is what the reason this process synchronization mechanism comes into picture. So let me erase this so that I can show you the slide. Yeah. So basically, we know that processes are going to execute congruently. Okay, we already know that the different processes are going to execute congruently. Like I told in the previous example, P1, P2, they are going to simultaneously execute on a same file or the resource, whatever they are using. So on the same file or the resource, they are going to simultaneously execute the operation. So whenever they're performing operations, what I said is that there will be a inconsistency in the data. Okay, that is what we basically call it as data inconsistency. So, okay, data inconsistency. So there will be a data inconsistency whenever we are performing the operation. So to overcome that particular inconsistency, we are actually applying this process synchronization mechanism. So in order to make you people understand it much more better way, I'm going to take the same example. I'm going to take an example and explain you so that you can understand how this problem actually exists practically. Now let us take an example. The previous example of your third unit, what we discussed is producer consumer problem. I think you people are very much familiar with it. Okay, so any of you are not familiar, don't worry, I'll just recall the steps. So here we have a producer, this is one process, we have producer process, and here we have a consumer process. So we discussed some points related to it. The producer will keep on producing, so we have a buffer here. This is the one which we call it as buffer. In between producer and consumer, we are going to have this buffer. Okay, let me write it here. This is your producer, this is your consumer, and in between we have a buffer. Okay, a buffer where we are going to place the items, whatever the producer is going to produce and whatever the consumer is going to consume. So we discussed it in the third unit that producer is going to produce the items, and that items we are going to store in this particular buffer. And what the consumer is going to do, he is going to consume the items whichever the producer has produced. And when we discussed this, we also said we also seen some logical programming diagram. I mean the logical part of this particular means coding part related to this particular producer consumer problem. Okay, if you are not aware of this particular programming part, that you people can refer my third unit so that you can the videos of a third unit so that you can get a clear understanding of this producer consumer problem. So here, what are the restrictions? What we said here is that that is related to this particular buffer. Whatever the buffer you people are seeing here, this buffer we actually classified into two types. Something we, if you remember, we classified into bounded buffer, and another one is what we call it as unbounded buffer. So I think you people are familiar with this. Bounded buffer is nothing but which has a limit. Bounded is nothing but which has a limit. Unbounded means no restriction. Unlimited, no restriction, or you can call something unlimited amount of. So based upon this buffer, I am mainly concerned about here. This one is as a bounded buffer because there is a limit here. So that's the reason I am going to focus on, and I'll explain it how the problem is coming when both the processes are trying to access the information simultaneously, execute using that resources simultaneously. So if you see here, when you talk about the bounded buffer here in this particular scenario, we know that whenever we are taking this, means it has this particular buffer will have some limitations whenever you're talking about bounded buffer, because there is a limit, maybe depending upon whatever the thing you're giving, 5, 6, 7 or odd. So it means only at a time 7 items can be placed in that particular buffer. And we know that whatever the size of the buffer is, we can store only buffer size -1. Buffer size -1 elements only we can store in this particular. Why he's saying like that is nothing but we can store 7 elements, so it means 0 to 6 we can store the information, right? Not more than that, because initially we start from 0. That's the reason from 0. That's the reason we are calling it as buffer size. Suppose the buffer size n is equal to 5. How many elements we can store is 5. But initially when you are representing, you'll represent from 0 to 4. Okay, so that these are nothing but 5 elements: 0, 1, 2, 3, 4. So if you see here 1, 2, 3, 4, 5, so 5 elements you are storing in your buffer. So this is what he's saying in this particular scenario. Now the problem here is how to determine, how the system comes to know whether the buffer is full or the buffer is empty. That we need to determine. And in order to do that, he is actually coming up with a solution, that is what we call it as counter. Yeah, he is using a counter. Counter is nothing but it's an integer variable. Okay, just let me clean it up. Yeah. So if we talk about this particular situation, something called a counter, this counter is nothing but it is an integer variable. The common variable what we use in our C programming and Java and all. Okay, now this counter variable will be incremented. This will be incremented or it will be decremented depending upon the operation whatever is performed. For example, the producer is producing. Okay, the producer is producing an item and that item we are storing in the counter. So what will happen? I mean, in the buffer, this is a bounded buffer. So what will happen? So initially 0. So when this particular thing is filled, we need to go to the next location in order to store the element created by this particular producer. So what we need to do? We need to do increment of this particular counter, C++. Okay, initially the value of C is, or the counter is 0. Now, what about when we will be decrementing this? I think you might have understood now. There is a consumer, right? He is going to consume the item from here. So whenever he is consuming one item from this particular buffer, so definitely what we need to do, we need to decrement, because that particular buffer is empty now. That particular slot, whatever the item is present in that particular slot, this is actually taken by this particular consumer for performing the operation. So what happens is this particular slot, it becomes empty. That's the reason we are doing C minus minus operation. Okay, so using counter, we will try to keep track of the number of buffers that are full and the number of buffers that are empty. Well, what is the problem here? What is the main problem? So main problem comes when producer and consumer at a time. Okay, at a time the producer is producing one item, at the same time the consumer is consuming an item. Then what will happen? Whatever the value of this particular counter is, that will not be in a specific order. There will be inconsistency in this particular counter value. Okay, and that is what I'm going to show you in the next slide. Okay, so let's talk about this particular diagram. Okay, logical part. Now this is the logical part after modification using the variable called as counter. We are using the counter. And as I told you in the previous slide, counter plus plus will be used in producer. So in order to increment the buffer to store the new item. Whereas coming to the consumer, the counter will be decremented because he has consumed one of the items from the buffer. So that empty, there is an empty space in the buffer. So to represent that, we are using counter minus minus. So let me explain this particular logic. It's very easy. So coming to the producer, while we are going to use a while statement. So while the condition is true, the system means the producer will enter into this particular logic and try to find out what he's going to find out while the counter is equal to buffer size. While the counter is equal to buffer size. What does that mean? Is nothing but, let us suppose the buffer size I am taking as 5. If 5 equal to 5, what does that mean? The buffer is full. There is no empty space available that the buffer can support. Okay, the producer cannot place the item in it because the buffer is full, the consumer haven't consumed anything. So what we need to do at that particular location is do nothing. The producer should not produce any kind of new items. Since that item cannot be placed in the buffer, so we should not do that. In case this condition fails, then we'll go to the next step. That is buffer in equal to next produce. So whatever the new item that we are going to produce, that item we are going to store in that particular buffer in. So I think you people might have understood till now what do you mean by buffer in. It is an array. of size what I am taking 5. So 0, 1, 2, 3, 4. So here in is nothing but it's a variable which is used to represent, like we usually use I, here we are representing in. So we are using two variables here. This I have already explained in your third unit, in and out. In represents whenever we are adding any element into this particular buffer, we'll use in. Out when we are using, when we are removing one element from this particular. So these two are variables we are using. Same like we use I and j variable, same in that way we are using in and out. So here what we are doing, buffer in equal to next produced, in equal to in plus 1%. So whenever we are adding an item here, so we need to increment the value of in. So initially in is equal to 0. So we have placed the item here. Next the in has to be representing 1. For that we are using this particular logic. In equal to in plus 1% buffer size. So it will be representing now 1. Counter plus 1. Now the counter value becomes 1. Initially it is 0, now it becomes 1. So in this way we are going to provide the producer logic. Okay. If you want a clear cut in-depth explanation of this particular logic, you can refer the third unit. It becomes much more easy. But anyhow, it is very easy to understand. Next one is consumer. How the consumer is going to do. First he will check the condition. If the condition is true, then he will enter into it. Here also he is going to check the condition, whether the buffer is empty or not. Counter equal to 0. What does that mean? There is no elements present in the buffer. So then what we have to do, simply the consumer has to wait until the producer is producing. In case this logic fails, means there exists some element, some item within the buffer and the system can access it. Then what we can write here is next consumer equal to buffer out. I think you might understand how we are writing it up. So using an example I have explained in the third unit, you can just refer to that. So here what happens, this one is for taking the elements out from the particular buffer and storing in the next consumer. So definitely the out has to be incremented to the next level where the element is present. So that is represented here. So out equal to out plus 1% buffer size. And finally what we need to do, since one element has been removed from the buffer, we need to decrement the counter. This is the way how we are going to perform the operation. But why the reason why I'm explaining this is, I will show you now what will happen if counter plus plus and this particular C minus minus, this counter plus plus and counter minus minus simultaneously executes, then what is the problem? If you see, if you execute them separately, like producer separately and consumer separately, okay, let us suppose the counter value is initially 5. Okay, the counter value is initially 5. If you execute them separately, what will happen? What will be the value of counter here? It will be in like something like no in between 6, 5 and 4. For example, initial value of the counter is 5. So if we execute this step first, then what is the value of counter now? 6. And after that, if you are executing counter minus minus, then what will be the value of 6? Will become 5. But this I am telling you one after another. But assume that both are executing simultaneously. Both are trying to execute simultaneously. Means when counter plus plus the producer is performing the operation, at the same time the consumer is also performing counter minus minus. Then what will be the value of this counter? So let's take C is equal to 5. Simultaneously I told you. So producer what he will do? He will increment it. So what is the value of counter here? 6. And at the same time consumer also have taken the value. So at that time the consumer will have the value of counter as 5. So what will happen when he is doing C minus minus, the value becomes 4. At a time you are having the value of counter as 6 and 4. Do you really think it's possible? It's highly impossible, right? Basically, if you're doing stepwise one after another, the actual value of your counter is 5. But because if this producer and consumer are trying to access the information simultaneously and execute the counter value simultaneously, what happened here? So there is an inconsistency. You can see the C, whatever the counter we have taken, there is an inconsistency in the data. Actual value what we need to get is 5, but simultaneously when they're executing it, producer is getting a value of 6, whereas consumer is getting a value of 4. There is a lot of data inconsistency here. There is no perfect value we have for this particular counter. This is a problem that we are facing. And to overcome this problem only, we are actually talking about this process synchronization. Yeah, here he has explained beautifully using the registers here. If you see the same, whatever I've explained you, this is represented practically here. So register is one is nothing but this is related to your hardware. In hardware, we generally have registers. And using that register, we are going to perform the operation. Now, what is saying registers, how they perform register equal to counter? this is related to your producer. Okay, this is related. These are machine language. Whatever you're seeing the steps here, these are not software based. These are machine language based. So whenever you complete writing the above code, what in the previous video, slide, what you have seen the code, that is a software based code. You might be writing in your C language or Java. But this one, whatever you're seeing, this is machine language. After compiling, this code will be generated by your assembly language. It is the one which is going to perform this. Same way, this is related to your consumer. Now, if you see here, at time, okay, S naught. So I have taken S naught here. You can also take T naught. At time T naught, producer executed. So producer executed the first step. Register 1 equal to counter. So I have taken the counter value as 5, right? So register 1 is equal to 5. At time T1 or S1, okay, producer executes. So again, producer is executing at time T1, not the consumer. So register 1 value is equal to register 1 plus 1. So what is the register 1 value we are going to get is 6. So right now the counter value, so register value is 6. Now what happened immediately? At time T2, what happened? Since producer and consumer are executing simultaneously, now at time T2 consumer was started executing. In the consumer's register, the value what we have is 5, but the actual value what it should have is 6. You can see there is an inconsistency here. Okay. And after that, I will show you the inconsistency where it is going to get exactly, because it is stored in registers. We can't say exactly here. Within the counter, when the values will come, then you can see. Then we have something called as consumer executes register 2 equal to. So at the time T3, consumer is going to execute it, and you can see that the value of register is 4. Okay, and S4 at time T4, counter is equal to register 1. So counter, the value of producer is getting the value of CS6. Here coming to a time T5, the consumer is getting the value of counter as 4, and that is what I have shown you on the previous slide. See here, producer is having the value of 6, consumer is having the value of 4, and this is what the problem we are facing here. So what happens? Actually, the value of C should be 5 for both the producer and consumer. Okay, you might be getting confused that we have used the two registers. Now, well, register 1 is equal to your register 2 is equal to represent to same hardware. Okay, just for understanding purpose, we have used two different registers as register 1 and register 2, but actually both represent the same hardware. That is what we have in your computer organization. You have something called accumulator. This is the one which we use to store the information, this counter value. Okay, so we have only one hardware. For that, I have represented using two different registers so that you can understand the difference. So register 2 refers to consumer and register 1 refers to something called as producer. So you can see there are two different values we have, but actual value should be 5. That data inconsistency we need to remove from this particular problem. Okay, that is what the problem we do have. So for that only we are going to coming to the next slide. That is nothing but your critical section problem. So what do you mean by critical section problem? Let me explain it before explaining the slide here. So critical section problem. Let me explain, flash some light on this particular critical section so that you can understand what do you mean by critical section. See, let us suppose that we within our system, your laptop or your lappy or something like that, you have n processes. How many processes? N. Something P1, P2, so on up to Pn minus 1 processes, UP plus. I'm sorry, we usually represent from P0 now, P0, P1, so on up to Pn minus 1. Now, every process, whatever is actually getting created in your system, will have some code segment. Every process will have a segment of code. We basically call it as a code segment or segment of code. Okay, this is nothing but small logic, something like, within the curly braces, whatever the data you're writing, that is what we call it as segment of code. And that segment of code is what we call it as critical section. Critical section. Okay, so what do you mean by critical section? Basically, this section is the one where the process is going to perform, where the process will perform different operations. So what kind of operations? Like updating tables or updating files. Okay, all these things will be done within this particular critical section. All these things will be done within this particular critical section. That is what comes under critical section. Means a very critical thing, means the main purpose why this process has been generated. that execution will be done using this particular critical section. And the thing here is that at a time only one process should execute. Means whenever one process is executing in the critical section, the remaining processes should not be allowed to enter into the critical section. At a time only this process should enter into the critical section, he has to perform the operation. Remaining processes should wait until he is leaving that critical section, then another process whichever is there that can enter into the critical section, perform the operation. So here the problem here is, what is the problem here is that how we need to design a protocol. Okay, sorry, we need to design a protocol. Okay, the protocol which should be taken care, means should be used by all the processes. All the processes should cooperate with it. So why we are designing a protocol? So that at a time only one process can enter into the critical section. The remaining processes wait until this particular process is leaving it up. That is the main reason we are applying this particular. That is a critical section problem. Okay, the problem. I think you might have understood what I explained till now. So here the critical section problem, what is talking about in this particular scenario is nothing but whenever a process, every process will have a code segment or segment of code, and that code segment is nothing but, okay, let me show you. So here you can see here we have n processes, as I told you, p0 to pn minus 1. So every process will have a critical section. Okay, and in that it is going to perform different operations, like it will be changing some common variables, updating tables, whatever the important content that particular process has to execute, that is represented in this. So whenever one process is executing in the critical section, then no other process should allow into the critical section. That is a thing. So what is the problem here is we need to design a protocol that the processes can use to cooperate. Okay, we need to actually design one particular rule that particular rule should be followed. Like for example, for you people, we have a rule that you people have to come sharp by 9 o'clock and you should come in college uniform, right? So this is the protocol here. That rule you people have to follow it. So by sharp 9 o'clock you should be in the campus, and at the same time you should be in a college uniform. You should not come in civil. That kind of protocol. So here also we are designing, but here the protocol is related to that at a time only one process can enter into the critical section. Remaining process should not be allowed to enter into critical section. So we need to design that particular protocol. So basically, yeah, we are going to design that, and in order to design that, we are going to have some three different type of sections. We basically call it as entry section, exit section, and reminder. Remember, this is a skeleton for your critical section problem, and whatever the solutions you people are going to show in the coming session, you are going to use the same skeleton. This is something like a syntax. Okay, let me show you the diagram so that you can get a clear idea about it. Yes, this is the diagram. If you can see here, we are going to use a do while statement here. So within that we have something called as entry section, exit section, reminder. And I think you people are very much familiar with your critical section. So any process which want to enter into the critical section. So what do you mean by entry section is nothing but any process which want to enter into the critical section, it cannot go directly. It has to first request for permission. It has to request for permission to enter into critical section, and that is what we call it as entry section. Every process must request permission to enter into critical section, and then only that particular, if the permission is granted, then only it can enter into the critical section. Until unless that time, it cannot enter into the critical section. Then we have exit section. What do you mean by exit section is nothing but once the process which enters into the critical section completes the task, he is going to come out. And when he is coming out, he has to release all the resources, and it has to intimate the remaining processes that I am coming out of the critical section so that they can be get ready to enter into the critical section. So that is what we call it as exit section. And after that, whatever the operations we need to perform, that we can perform using the reminder section. Whatever the last scope of the things, whatever we have, that can be implemented using this particular reminder section. And remember, we are going to use something do. Now, this is a basic skeleton what you people are going to use in the coming slides. Okay, so please don't forget this, and please remember it. It's very important. These two sections are represented in a rectangle box because these are very important segment codes. They are very important segment codes. because based on that only we will be allowing to enter into the critical section, and when the process exits from this particular section, then only another process can enter into the critical section. That's the reason these are very important segment codes what we do have. I hope it's very clear with respect to this particular critical section problem. So here, so we need to provide a solution to this particular critical section problem, right? For that, they have actually provided three properties, you can say. They actually provided three properties or three requirements. We basically have three requirements. So anybody, if anyone is providing a solution to this critical section problem, I mean they are designing the protocol, that protocol should satisfy these three requirements. And if it is satisfying it, then that is a perfect solution to the critical section problem. So what are the requirements we have here is, first one is mutual exclusion. Mutual exclusion, progress, and then last but not the least is bounded waiting. Yeah. So if any of the programming solution you people are designing, okay, for this particular critical section problem, that critical section problem should, that solution should satisfy these particular three different type of requirements. First is mutual exclusion, progress, and bound wait. Let's discuss about them. What do you mean by mutual exclusion here? So as I told you, we have, okay, let me erase it so that you can see it clearly. So first is mutual exclusion, progress, and then we have something called as bound waiting. What do you mean by mutual exclusion is that nothing but already I told you, if a process Pi is executing in the critical section, then no other process J should not be allowed to enter into the critical section. Okay, that is mutual exclusion. If your program, whatever the logic you're writing, satisfies this requirement, you can say that is a solution, good solution. Then we have something called as a progress. Progress is nothing but if no process actually taking part in critical section, means no process is executing in the critical section, but some processes are ready to enter into the critical section. So since I'm talking about some process like P1, P2, P3, there is a critical section. No one is executing. Means all the three are ready to enter into the critical section. But what did we say? At a time, only one process can get this critical section for performing the operation. So these three processes will enter into a meeting. Yes, they will keep a meeting, and within the meeting they will decide which process will go first, P1, P2 or P3. And once they have selected that particular process, he has to go for sure. He cannot say that no, I will go next time. No, he can't say. Once it is decided that process P2 should enter into critical section, then P2 should definitely enter into the critical section. That is what comes under progress. And remember, which processes can participate in this particular meeting is nothing but the processes which are not executing in your exit section. Okay, the one which are not executing in the exit section can participate in it. Remaining cannot participate. Okay, so whichever are not executing in the exit section, they only can participate. Remaining people, they can't do it. And what about the next one we have here is bounded waiting. So coming to the bounded waiting here, so what I mean is to say that every process which is actually entering into the critical section, they generally have a limit. Bound is nothing but limit. So the number of times this particular process P1 can enter into the critical section will be limited. Okay, so whenever it makes a request to enter into the critical section, first the operating system will decide how many times this particular process has entered into the critical section. If he has executed the limit, then definitely the operating system will stop this process from entering into critical section, and it will give the other processes the chance to enter into this particular critical section. So whenever you people are actually creating any kind of solution, that solution should basically satisfy what it has to satisfy, nothing but all these requirements: mutual exclusion, progress, and bound waiting. If all the three requirements are satisfied to the solution you people are providing for the critical section problem, then definitely it is a perfect solution. It is a perfect solution for your hardware. Okay, it's a perfect solution for your critical section problem. This is what he's talking about in this particular scenario. Now, okay, just let me erase it. So there are basically two approaches that have been used here. Okay, let me first erase it up so that, yeah. So basically, in order to implement this particular critical section problem, we are going to talk about some two different types of approaches. We have two approaches. So we are going to discuss about two different type of approaches here. The first approach is primitive, non-primitive. I think you people are very much familiar with this terminology. Primitive is nothing but the one which will frame it. So here, whichever the process is executing in a kernel mode, the process is executing in a kernel mode. This particular process can be preempted whenever a high priority process comes. Suppose P2 is having high priority than P1. Then P1 can be preempted by the operating system and the resource of the CPU can be allocated to P2. That is what comes under primitive. And another one is non-primitive here. So what do you mean by non-primitive here is nothing but whichever process is executing, once the process is allocated to the critical section, no other process, even a high priority process is coming, he is also not having the right to preempt this particular process. Whenever this process is voluntarily releasing this critical section, then only it can be allocated to P2. That comes under non-primitive. Okay, so these are the two approaches that are used in order to implement this critical section problem. But here the thing is, if I ask you which one is much more better, primitive or non-primitive? Well, mostly everyone will say that primitive is much more better. Okay, sorry, non-primitive is much more better. Why? There is no race condition for this. We don't have a race condition here, no race condition. What do you mean by race condition? That no process, once the process is allocated to the CU, if P2 is coming, he knows that this is allocated to him, he will sit idle. P3 is coming, he will sit idle. No one will compete to get this particular critical section. Why? It is already allocated. So that's why, so what happens here in non-primitive, we don't have any race condition. But if we talk about the primitive here, yes. But among primitive and non-primitive, primitive is much more efficient. Do you know why? The reason is, let us suppose this particular process we have allocated to the critical section. He requires, like in the second unit we discussed about process scheduling. This particular process requires 2 hours to complete the task. Then another process came, he requires only 10 minutes. Another process came, he requires 20 minutes. So what happens here? This P2 process, his task is only for 10 minutes. But since the critical section is given to this particular process P1 for 2 hours, he has to wait for 2 hours 10 minutes to complete the task. Same way, what about this particular P2? He has to wait for 2 hours 30 minutes to complete the task because 20 plus 10 is 30. So 30 minutes. So unnecessarily P2 and P3 are waiting for additional 2 hours of time. So in order, so that's the reason in real-time operating systems, primitive is much more better when compared to your non-primitive approach. Okay, I hope it is very clear till here. What do you mean by critical section? So what are the requirements are there in order to generate a solution? So whatever the solution we are generating for a critical section, it should satisfy these three parameters. That is mutual exclusion, progress, and bound waiting. So we will see one solution here. Okay, so we are going to discuss. So with this, we'll complete the session. So Peterson solution. This is actually a software-based solution here, not a hardware-based. It is a software-based solution. And within this, well, this cannot be implemented. This cannot be implemented in today's real-time operating systems. Yeah, whatever the architectures we have in today's scenario, we cannot implement it. Why we cannot implement it? This solution is only for two processes, P1 and P2. Generally, we represent P0 and P1. So this solution he has been given where we can apply when there are only two processes within a system. But today's systems, whatever operating system we are seeing, it supports around multiple multiple processes. Not only two processes, multiple means minimum 100, like something like 100. Okay, 100,000 processes at a time we can see. Okay, within our own system itself, you can see some thousands of processes getting executed simultaneously. So you can't apply this particular Peterson solution to those particular things. But why we are discussing this? Yes, there is a reason why we are discussing this, because the way the algorithm is designed and its description is perfect to understand and generate a new kind of algorithms. Yeah, and moreover, how the complexities we have, the complexity that we have in order to design this particular software-based solutions. Okay, so whenever you're designing a software-based solution for a critical section problem, what are the complexities you people will be having? That he has explained very nicely in this particular concept. And that's the reason we are actually discussing this particular concept. Yeah, that's the reason. Or else we in today's world, in your laptop, you're not going to apply this Peterson solution because it can be applied only for two processes, P0 and P1. So it's highly impossible to implement it. So if you see here, okay. So basically, okay, I need some space here to write. Okay. So this is a classical software-based solution that we already told you, Peterson solution. It is the name, the person who developed it is his name is actually Peterson. Sorry. So that's the reason we are calling him as Peterson here. Now this is actually restricted. So basically, as I told you, it is actually restricted to two processes here, P0 and P1, and within that only we are going to perform it. Now before discussing about this particular Peterson solution, let me define the data structures. We are going to use two different data structures here. Data items, int, term, and boolean flag. So basically, if you can see, if you people are very much familiar with your C programming, you can understand this is simply a declaration of a variable of type integer, and this is a declaration of an array of type boolean. Means this will have either the value of 0 or 1. That's it. And whereas coming to turn, this is a variable of type integer. Now, what is the main purpose of this turn is to indicate whose turn it is to enter into the critical section. Okay, so whose turn it is to enter into the critical section, that is the main task of this particular thing. And whereas coming to means, if for example, if I'm writing turn is equal to I, so that means PI will enter into the critical section. If turn is equal to J, then PJ will enter into the critical section. Same with flag. Flag is used to indicate whether a process is ready to enter into the critical section or not. For example, if I'm writing flag of I is equal to true, it means this particular process Ti is ready to enter into the critical section and is waiting for its turn to enter into the critical section. Same if I am representing flag of J is equal to true, means Pj is ready to enter into critical section and is waiting for its turn to enter. That is what represented in this particular scenario. So these are the two data items what we are going to use, and based on that, this is the data structure. I think you people might be familiar with the critical section skeleton. So this is your entry section. And here you have something called as critical section. We did not write any code here. You have to write code whenever you're programming it. And this is, I'm mainly focusing on entry and exit section. Okay. So initially what we have written, if a process PA want to enter, so flag of I is equal to true. What does that mean? That this particular process PA is ready to enter into the critical section. But before entering into the critical section, he is giving a chance to the next process, whatever is having. Turn is equal to J. Means if the J is ready to enter into the critical section, he can enter into the critical section. That is what he's saying in this particular scenario. So this is a condition which decides whether a process will enter into the critical section or not. While flag of J and turn is equal to J, both the conditions are true, then only a particular process can enter into critical section. What is saying? If flag of J is true, 1, and turn is, if it is a J's turn, then PJ will enter into the critical section. And once he completes the task, when he's coming out, he will say flag of J is equal to false. Means he is making himself false. I mean he is not ready. Not just now he came out of critical section. How can he be ready to enter into critical section? So he is making himself false. Means he's saying that I'm not ready to enter into critical section, and he will come out of it. So then comes the remainder section. The remaining portion will be done. Okay, so based upon this entry section only, you're going to perform the operation here. You can see here, and we're just coming to this particular thing. So here, what he's saying is, we need to make sure that all the three cases, whatever I extend requirements, mutual exclusion, bound waiting, and the last but not the least is, progress. All this we need to satisfy. Now, well, I'll explain it so that you can understand here. If you see here how this particular thing is satisfied, let me explain it. If you see this particular PI enter into the critical section, right? Critical section. If you see here, let us suppose the process PA want to enter into the critical section. So flag of I is equal to true and turn is equal to J. In case PJ wants to enter into critical section, then turn is okay. This is 1. But what about flag? If flag of J is also true, then that particular process J can enter into critical section. What about PI? It cannot enter into the critical section. So at a time what happens? Only one process can enter into the critical section. Why? Because flag of I is equal to true, but the turn we gave is J. So who can enter into here? I can enter into the critical section, not J. Once the person is coming out of it, then flag of I is equal to false. Flag of I is equal to false. So then what will happen? Then flag of J will become true, and the turn is already J. So then process J will enter into critical section. So at a time only one process can enter into the critical section. So this way the mutual exclusion is satisfied. And what about the bound waiting and progress? Well, that is also satisfied because at a time one process is entering into the critical section. So these both processes are deciding which one. If P0 wants to enter into critical section and it is decided P0 will go, then definitely P1 can't go. And if P1 decided to enter into the critical section, P0 will not go. So this way we are actually satisfying your bound waiting and progress. Okay, and if you see here, when P1 has entered into a critical section, next time definitely P0 will come into the critical section. P1 cannot come into the critical section. Why? The flag here, this one, we are telling it as false. He is not ready to enter into critical section. So there is a limit that at a time only one process, one at a time. So whenever this person P1 is getting a chance, after that immediately P0 should get a chance to enter into critical section. So we are bounding the limit the process P1 is entering into critical section. Means when P1 is entering into critical section, he is coming out. Again, P1 cannot go into the critical section. So there is a limit here. Only P0 can go. After P0, P1 if he wants, he can go. So this is what how the three conditions are satisfied. Okay. I hope it's very clear till here. You might have understood this particular concept. So this Peterson solution we are not going to imply in our what we call the latest laptops whatever we do have, but this is one of the beautifully explained concepts because of which based on that only we are going to see the remaining concepts. That's the reason we are discussing this particular concept. So remember, the coming scenarios, whatever the solutions we are going to discuss, that will be based upon this particular thing. So we will be having something called as entry section, critical section, and exit. We are going to design this particular logic. Internal critical section, whatever the task they want to do, they can do it. But the main focus, what we are going to see in the coming scenarios is entry and exit section. Based on that, this particular process will be allowed to enter into critical section. So I hope it's very clear. With this, you might have understood the concept very well. If you have any doubts with this, you can just ping me up. Okay, please don't, if you have any doubts, you can directly ping me up on this particular numbers. Okay, thank you for watching. In the next session, we'll discuss about the remaining portion of this particular unit.